Okay, so the way this works with the grand unification theory is that gravity strips off first. It was originally part of the four forces were part of one super force, if you will. Gravity peels off first in the early moments of the Big Bang, and then the strong nuclear force peels off, and then the electroweak and I'm sorry, the electroweak is actually two forces: the weak nuclear force and the electromagnetic force. Those two actually have been united. We can experimentally prove that there is such a thing as the electroweak force, which gives us gives this grand unification theory at least a footing, because we've at least experimentally proven part of it. All right, so let's go on to the next thing. All right, so the next era after the Planck era is called the quark era. Okay, so quarks are the things that the primary thing for the universe is that quarks create the protons and neutrons. All right, so that's there's three of them, three common ones that make up protons and neutrons, and so during that time, these elementary particles are basically in equilibrium with the radiation. They're created just as fast, right? Remember, it's pair production, so a quark and an anti-quark are there's 6 different types or flavors, if you will, of the quarks. Anyhow, again, this is not really a course on elementary particle physics, but it is related to the creation of the universe as we know it. Anyhow, you have these things are created. These quarks are created just as quickly. They're eliminated because the strength of the radiation is so strong. But then, as the universe cools, as it says here, the photons are no longer producing these heavy elements, and the quarks freeze out, right? Of course, the lighter things, which are collectively called leptons, so these are electrons, positrons, right? That's just the antiparticle of an electron. Things called muons, and there's actually another one called tau. Anyhow, like a muon is just a heavy electron. A tau is a heavier muon, basically. And of course, neutrinos, right? Neutrinos are a huge part of the universe. Although these are very elusive particles, they travel almost at the speed of light. Remember, they come from nuclear reactions. Anyhow, the next era after the quark era is called the lepton era. That's when the electrons are created. Then we have about a second or so after the Big Bang becomes transparent to neutrinos. So some of the neutrinos that we've detected, and remember, it's very hard to detect these things. Not only is it hard to detect them, we can't distinguish between, at least right now, and it would be really nice if we could do this, but we cannot distinguish between neutrinos that were created a second after the Big Bang and ones that were created yesterday in the sun. Okay, but again, it's always hopeful that there'll be some kind of experimental method which we could distinguish those. That would actually be really good, because that would give us a sense of what the neutrino density was in the early universe. Anyhow, that's just an interesting side. About 100 seconds after the Big Bang, photons become too low energy for the electron and positrons. So basically, after that time, all the electrons that are ever going to be are created. At that moment. to some extent, not that's not exactly true, but for the most part it is, right? So the vast majority of the electrons and protons have already been created at this moment, and this is in this once after about 100 seconds, that ends what's called the radiation era. That is where the radiation density was greater than the density of just normal matter, and in fact even the dark matter too. So we can so this 100 seconds, a long time ago, I read this book. It was actually fascinating, although it probably needs to be updated, but it was called The First 3 Minutes, which the first 3 minutes is basically this 100 second period, or not exactly that, but back then it was called the first 3 minutes, and this is basically what that book was talking about, is what was going on during the radiation period, and there were some really important events taking place, and some of that we can still look out into the universe and get a sense of what the universe was like in that. From the way the universe is, as opposed to the way the universe isn't, we can get some sense of what was going on. All right. Anyhow, so the photons. So in this next era, the photons are no longer ionizing the atoms. They're no more able to ionize atoms as soon as they form, and so this next era is really the point where hydrogen and helium atoms begin to form. Okay, so this is actually a really important step. Let's see. Does the next? Let me look at the next. Yeah, this is going to go back. Hold on. What's after this? Yes. I thought we were going to talk about. All right. Anyhow, since I'm mentioning this now, so hydrogen and most of the helium, not all the helium, but hydrogen in particular is the original atoms, right? The primordial atoms that were created, right after the Big Bang. And so helium atoms were also created during the Big Bang, but before the helium atoms come into existence, hydrogen atoms. Remember, hydrogen is just a proton, right? But remember, during the quark era, there are quarks that are eventually going to form neutrons as well as protons. And so there's neutrons available, and so some of the hydrogen. Remember, the universe is very tiny at this point. It's very, very hot still. Some of the hydrogen will fuse with neutrons, right? So in other words, it becomes this thing called heavy hydrogen, which has actually hydrogen 2, it's actually called, where there's a proton and a neutron that are bonded together. And by the way, that actually has a name. It's called deuterium. And deuterium. So why are we interested in deuterium? Well, it turns out that when we look out into the universe, right, we see that the stars, like, we never find stars that have a smaller percentage than about 25% of their mass in the form of helium, right? Like, we never find a star that has let's say 15% of its mass as helium. It's always 25% or more. Okay, so the more part is really important. Like our sun, for example, has, I think 28%, 27 or 28%. So basically 25% of the helium is original helium, the helium that came out of the Big Bang itself. Okay, So the reason that I mentioned the deuterium, right, which is heavy hydrogen, is we cannot distinguish between helium that was created during the Big Bang, although we know that there was, roughly 25% of the helium that's out there was created during the Big Bang. But we can't distinguish between a helium atom that was created then, right after the Big Bang, and one that was, again, created yesterday, like in the sun when hydrogen fuses into helium, which is, remember, that's the source of a star's energy for most of during its lifetime, right? It's converting hydrogen into helium. So there is this increase in helium that's been going on for the last 13 billion years. So we don't have a way of distinguishing between helium that was created yesterday as opposed to helium that was created almost right at the very beginning. But we do, the deuterium that was created actually gives us a good indication of, we can detect it out there in space, and we can detect the amount of deuterium that's out there. Because, see, deuterium, unlike, deuterium is not created during the normal fusion process. And so the deuterium that we detect is primordial primordial deuterium. It was the original deuterium that was created, when 25% of the hydrogen atoms became helium. So there's some small fraction of the hydrogen that became deuterium, and so that is unaltered. That fraction of deuterium has been unaltered since the Big Bang, or just slightly after the Big Bang. All right. Whereas the helium, of course, is constantly increasing as time goes on. All right. So that amount of deuterium is a really important indicator about what was going on in the very early universe, and of course what the overall density of the universe was back in early times. All right. So fast forward, we're going to get more into this in a little bit more detail, but during the next 3 billion years or so, you get galaxies created, quasars, and this is really in the three general areas where you had, remember, the radiation time, and then there was matter. And this is the time, this first 13 billion years is the time of matter, right? Where matter has the most density of any of the different forms in the universe. And then, of course, nowadays, and really since this last, since 13 billion years after the Big Bang, we've been just recently, in the last few billion years, we've been in what's called the dark energy era. All right, so so after galaxies evolve, we see star formation taking place. And in fact, by the way, just to let you know, one of the big ideas now is where the dark matter is has a lot to do with where galaxies form, because we'll get more into this when we talk about the cosmic background radiation. All right. So anyhow, we're in the middle of what's called the stellar epoch. This is where the most stars are being created. Of course, there's stars being created today in galaxies that still have lots of gas and dust available. Especially, like, for example, irregular galaxies, which half their mass is in the form of gas and dust, or when there have been galactic collisions. And so this really indicates the time when there were a great deal of galactic collisions. Remember, that's when the starbursters, these galaxies that collided and merged, and there was incredible amounts of star formation. All right, so here are the forces in nature in order of strength: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity.